share my screen. And get right at it. So last time we were discussing buffers and how to make buffers and how they work and so forth. So this is a good spot to start, I think. And here we have pretty much the definition of a buffer is any weak acid in the presence of its conjugate base. So you might say to yourself that a weak acid like HF, you put that into water and this equilibrium ensues. So it fits the definition of a buffer. So I have some weak acid and some conjugate base. Now, anybody out there see why this would be a terrible buffer? In other words, they wouldn't be able to maintain the pH very much. What am I missing? Yeah, it's kind of subtle. The thing is that this is a weak acid, so if I have a 1 molar solution of HF, it's pretty much 1 molar HF. And there's very little F minus. So even though this fits the definition of a buffer, it would be a horrible buffer because it doesn't have any buffer capacity. So this gets into, what buffer capacity is and why it's important, and how you'd fix it. So the moral of the story is, yeah, you can have a weak acid, but there has to be a significant amount of conjugate base and a significant amount of HX. And so when you have a significant amount of both, then when, say, a strong base is introduced into the buffer system and that weak acid gets consumed and produces a little bit of HX, or sorry, X minus, the conjugate base, the pH doesn't change because there was a lot of HX in there and a lot of X minus. So the changes are small compared to what the concentrations are. Whereas if you just took a weak acid and you threw it in water, the conjugate base, when it comes to equilibrium, is going to be very tiny. And so any little changes in its concentration is going to make a big difference. And same thing over here. And that's how a buffer works. A buffer works because there's so much weak acid and conjugate base in that equilibrium that when it absorbs a strong acid or it absorbs a strong base, the changes in their concentrations are small, and that results in a small change in pH. So that's important to understand, I think, and we get into that in a little more detail in the next few slides. But this slide here, I just recopied from a previous slide from the last chapter because it's important. This slide here shows us that if we have a weak acid and we have its conjugate base in equilibrium, and then there's a strong acid or base introduced into that equilibrium, then the first reaction that takes place is to completion. And all of the strong base and all of the strong acid should be absorbed. And we produce a little bit of the conjugate in that absorption. And that's the completion reaction. And that's the first thing that we have to understand. And the reasons why these are completion reactions is because they have strong or large equilibrium constants, which tell us that the equilibrium lies way to the right. And then last time we looked at how we can track the changes in the pH and maybe understand how a buffer works. So we took the equilibrium expression for Ka and we rearranged it to solve for H plus, because we know that the pH is connected to the concentration of H plus. And so when we looked at the way a buffer works to absorb acids and bases, we said, okay, well, if this buffer, which is made up of a weak acid and its conjugate base, if, say, you add a strong base to it, then this concentration of the weak acid is going to go down. This concentration of the conjugate base is going to go up, because that's what the reaction is that takes place. So one goes up, one goes down in this ratio here. So that means this concentration of H plus should change and the pH should change. And it does for a buffer. The pH does change, but it changes very little. And the reason is because you load up that buffer with a lot of weak acid and a lot of conjugate base. And so the question is, what's a lot? A lot compared to the amount of acid or base it absorbs. A lot compared to the change in its concentration. And then we looked at a quick example. You know, if I have a ratio of 2/2 representing this ratio here of weak acid over the conjugate base concentration, if one goes up and the other goes down, then 1 doesn't equal 3. That's a big change. But if I loaded it up with a lot of weak acid and a lot of conjugate base, and it goes up a little bit and the other one goes down a little bit, then hey, that's pretty much the same. And so that's how you have to think about a buffer, especially when you're going to make it up. And that's a reason why just throwing a weak acid in water and letting it come to equilibrium with its conjugate base, even though that is the definition of a buffer, that's a horrible buffer. It doesn't have any capacity. It'll change the pH upon absorption because it just doesn't have enough of one or both of the components. So we talked about that, and I think this is pretty much where we left off. And remember, the moral of the story is you need a lot of weak acid and conjugate base in your buffer. What's a lot? A lot compared to the amount of strong base or the amount of strong acid that you're expected to absorb, because upon absorption, one of those is going to go up, the other one's going to go down, but the relative amounts of the two are still pretty much the same. Any questions on that fairly subtle but important point?
I have one question. I guess by a lot, like what's an example of a number comparison between?
Yeah, the number of comparison, that's what I was trying to do back here with the 2000 over 2000. So a lot would be a lot compared to how much you're absorbing. So 2000 is a lot compared to absorbing 1.
Mm-hmm. Would 1,000 be a lot?
Yeah, okay, I see where you're getting with this, and I appreciate that question. So let's go onward and talk about um, this next thing called buffer capacity. And a lot can be arbitrary, and a lot, as defined by your textbook, is plus or minus 1 pH unit. So that ties into the definition of buffer capacity. So buffer capacity is related to the amount of acid or bases that can be neutralized before there's a significant change, a lot. So what's a lot? How much? Your book says that a lot is plus or minus 1 pH unit. So when that concentration changes enough to change the pH by 1 pH unit, then that's a lot.
Oh, okay. That makes sense. Thank you.
Yeah, sure. So, and it seems kind of abstract right now, but when we get into some examples, then you'll see how it changes with changing concentrations due to absorption. And then you'll kind of get a feel for what a lot is. So right now we're just talking about definitions and words. We haven't got into the math yet and the numbers. So when we do that, keep that in mind, and we'll hopefully hammer out this cloudiness that we're at right now. And then if you have a question still after that, then ask again. All right. So now we know what buffer capacity is according to your book, but hey, it's kind of arbitrary. What's a significant amount of pH change? Well, it depends on the experiment you're doing. If you want to maintain a pH around 7.4 units because some reaction takes place more efficiently, what's a lot? What's a big change? Well, maybe that reaction will still take place um, to a significant amount at 8.8 pH units. So maybe a change of plus or minus 1 is not really applicable to your situation. So it's arbitrary, but your book says, okay, you got to keep it in mind. So let's just pick a change, and we're going to say it's plus or minus 1. So that corresponds to these guys here, these deltas. So, for example, if a buffer has a weak acid, HA, and it absorbs a strong base, its concentration is going to go down by some change, delta. And therefore, the concentration of the conjugate base is going to go up by some delta. So a lot would be and that a lot would be, something that's going to change that pH by 1 unit according to your book, and that's connected to the amount that's absorbed. Okay. All right, so we're still not looking at numbers yet. We're still in the theory and the equations and stuff. And I will just want to do one more before we get to some examples of how buffers work, and that is the Henderson-Hasselbalch equation. Now, the Henderson-Hasselbalch equation is an equation that helps you understand how buffers work to maintain that pH upon absorption of a strong acid or base. And the Henderson-Hasselbalch equation also helps you make up buffers. And so to derive this so-called Henderson-Hasselbalch equation, which, by the way, is right down here. In short, it just looks like this. To derive that equation, we start again, and I say again because this is how we talked about how changes in pH can be tracked with a buffer by looking at the Ka expression, which is defined by the law of mass action, the concentration of the products to their stoichiometric coefficients over the reactants to theirs. Then we solve for H plus because we want to track changes in pH. And then the Henderson-Hasselbalch equation takes it a few steps further and says, okay, I know what pH is, so I'm going to take minus the log of both sides over here and over here. So I get minus the log of H plus, and then I can use a law of logs that treats the Ka separate from the ratio and just say Ka is times that ratio, and I can split it out, and that equals the log, or minus the log of Ka minus the log of the ratio. And I can identify now this term with the pH, and I can identify this term with the pKa, and that just leaves me with this guy right here, but they didn't like the negative sign. So they used another law of logs just to flip the ratio and turn that negative sign into a positive sign. And so now you have the Henderson-Hasselbalch equation, which tells you how the pH of a solution made up of a weak acid and its conjugate base is related to the pKa of the acid in the equilibrium, plus the log of the concentration of that weak base over the concentration of the weak acid in the buffer. So now you have all these components represented in the Henderson-Hasselbalch equation. And so now we can use that Henderson-Hasselbalch equation to, for example, make up buffers in the lab if you needed to. Okay, so I'm going to just write down that Henderson-Hasselbalch equation again. pH equals the pKa plus the log of the concentration of the base over the acid. And so now if your instructor in biology says, okay, we're going to be growing these animals in a petri dish or whatever, and we need to put in a buffer to maintain a pH of, I don't know, 8.5, then you know that's the pH that you want for your buffer. So I can put that number in. And now what you should do is you should now look up weak acids. Specifically, look up the pKa of weak acids that are as close as possible to the pH of the solution that you want to make a buffer for. And the closer these two guys are to each other, let's say I found one exactly the same, if that was possible, then what does this ratio have to be? The concentration of the weak base over the concentration of the weak acid. What does that ratio have to be for this to be true? Well, this term has to equal 0, right? The log of what equals 0? The log of 1 equals 0. That tells me that the concentration of A minus has to equal the concentration of HA. And that's a good thing for buffer capacity, because the closer they are in that ratio, remember we just picked 2000 over 2000, the better that buffer is going to be, the closer these two numbers are to each other. And we already know that they have to be large. That gives a good buffer capacity, when those guys are large and close in value. Because when one goes up and the other goes down, that ratio is less likely to change. Uh, so that's how you'd use the Henderson-Hasselbalch, for example, to make a buffer. Again, you pick your target pH that's based off of your experiment or that environment. This you look up in a table of pKa values. And you want to get that as close as you can to the target pH of the buffer you want to make. And the closer you get it, the closer that these concentrations can be the same. And that helps with buffer capacity. And then you just add in that other criterion that they both should be large. All right. Now, we're going to get to buffer problems and how to understand and look at the way that buffers absorb either strong acids or strong bases and the consequent changes in the pH. So before we get to this, any questions so far? All right, give me a chance to get a drink of coffee. All right, so a buffer and how it works again. So in this buffer here, I have a weak base X minus and a weak acid HX. So you know, in this buffer system, I have HX in equilibrium with X minus. So that's my buffer system. And it's in place. I made it up. I have the concentration of HX very close to X minus because I picked the weak acid with a Ka that's pretty close to the target pH of the buffer that I want to make. So I know those concentrations are going to be a lot and they're going to be around the same. So now it's in place. It's in my fish tank or it's in my agar dish. And how's it going to work? Well, if that thing is outside and get some acid rain on it and acid is introduced into the system, the conjugate base is going to react with that acid to produce the weak acid and water. And it's going to be a completion reaction because there's a strong driving force for making water and a salt. We looked at the equilibrium constants for these type of reactions. Or if that buffer instead is absorbing some base, maybe from the beasts that's inside of it, so it's got some base that it has to absorb, the weak acid will react to completion. Strong driving force for making water. We looked at those equilibrium constants. They were enormous. And water and a salt is the result. So the concentrations of the weak acid and the conjugate base change. But because we had so much in there to begin with, the ratio doesn't change much. And so the pH won't change as much. The pKa is just a constant, right? Once I pick that buffer system, once I've identified the weak acid in the buffer system, then this is just some number. All right, so the buffer system is in place. How does it going to work? Number one, Chem 200 problem, limiting reagent to completion, absorption of that acid or base. And so I have to find the new concentration of the components in the buffer after absorption, because one of them's going to go up and the other one's going to go down. That's the first problem. So a buffer problem really is the 1-2 punch. It's two mini problems that you already know. One, Chem 200 limiting reagent to completion. This guy is the limiting reagent here, that external additional acid or base that's added into the buffer. That's the limiting reagent. That gets absorbed, it's gone. It's got to be a small bit, or the buffer's not going to work. And that happens to completion. So Chem 200 completion reaction, you recalculate the concentrations, and then it becomes a Chem 201 second semester. You can use an ice table, or you can plug it into the Henderson-Hasselbalch. You get the same answer. And the reason is that although these should be equilibrium concentrations here, right? They're not. Say this buffer absorbed a strong base. So the equilibrium concentration of X minus would be some little bit more. And the equilibrium concentration of HX would be a little bit less if you did the ice table. But remember, these guys are weak acids and bases. We expect these changes here to be negligible. And then we check the 5% rule. So if you use the concentrations that you calculated after absorption and not the equilibrium, it's pretty much the same. But if you did it in the ice table, then you'd know to check the 5% rule. So the ice table is a little safer approach than just plugging it into the Henderson-Hasselbalch equation. All right, so again, we haven't even looked at any numbers yet or solved any problems. This is all theory, equations. I'm just trying to help you understand the whole forest before we get into the trees of those numbers and solving problems. And as always, if you have any questions, just holler. Okay, so here's our first example of a buffer problem. Okay, so in this example, it's kind of oversimplified because, well, you'll see. It says a buffer with a pH of 4.74 has 0.3 moles of acetic acid and 0.3 moles of sodium acetate. I want to ask you guys out there, see if you're still paying attention. What is sodium acetate? What kind of a compound is it, and how does it fit into this problem? What does it compare to, for example, acetic acid?
It's the weak acid conjugate base.
Correctamundo. Now, I know from Chem 200 that 0.3 moles of the sodium acetate, once it's in water, there isn't any 0.3 moles of sodium acetate in that form. What form is it in? All right, you guys. Go ahead.
It dissociates into its ion.
Yes, and you should know that from Chem 200. So if you didn't know that, then it's not my fault. It's your Chem 200 teacher. So you know that there's no 0.3 molar sodium acetate. It's 0.3 molar sodium and 0.3 molar acetate. I'm just going to put A minus. That's the conjugate base of a weak acid. So do I have to consider the effect of sodium Na plus in this aqueous situation?
No,
I can ignore it. No, why can I ignore that?
because it's a spectator ion.
You are correct once again. Thank you. So I just need to consider the weak acid that was added, aqueous, and its conjugate base. It also told me that they're the same concentrations, right? They're 0.3 molar. It's 0.3 moles in 1 liter. That's 0.3 molar of both of those. So I know if I want to calculate the pH of this solution, I know those concentrations are the same. So the pH equals the pKa plus the log of 1, right? They're the same concentration, so this is a big 0. So I know the pH is the pKa. So if you look up the pKa of acetic acid, it better equal 4.74, okay? And it does. So this is just background. But anyway, that's all in the buffer, and that's all well. Somebody needed a buffer that's going to maintain a pH about 4.74, so acetic acid is the choice. All right, so now the problem says find the new pH after 0.02 moles of a strong base is added. Assume no changes in volume. That's because you're going to have to work out changes in volume later. This is just an initial problem to show you how things are going to work. All right. Now, this 0.02 moles of sodium hydroxide is entered into this buffer system. My question to you guys is, what's going to happen to, well, first of all, sodium hydroxide, again, we get the spectator, Na plus and OH minus. Na plus we can ignore. So it's pretty much what they're telling us is 0.02 moles of OH minus hydroxide is entered into this buffer. What's the buffer going to do? Does anybody know? What's it going to do with that hydroxide?
Turn it into water.
Mm-hmm. And anything else? Yeah, it's not.
Yeah.
Yes, the conjugate base. It's going to turn it into water because it's going to react with the acetic acid, right? The HA plus the hydroxide. Is that going to be an equilibrium? No, we know that that's going to be a completion reaction, but I'm going to generate some A minus and water. Right? Does everyone see that? That's where you're supposed to say yes.
Yes.
It's a tough crowd out there. Okay, thank you. Yeah. Okay, so my HA is going to react with that hydroxide to produce A minus and H2O. How much A minus am I going to produce in this Chem 200 Livning reagent to completion initial reaction?
0.02 molar.
Yeah. And you know that because that's the amount of OH minus and it's the limiting reagent. And how much of HA am I going to lose?
.02.
Yes, the same amount. Thank you. So now you know that the concentration of that weak acid has to go down because it reacted, and it goes down by 0.02 from 0.3. And the conjugate base has to go up to 0.32 from 0.3 for the same reason. It's the Chem 200 limiting reagent. Then it switches in the Chem 201 ice table, or you can put those initial values into the Henderson-Hasselbalch and you get the same answer. Why? Because you ignore this pretty much and check the 5% rule when we do the ice table. But I'm saying the good thing about using the ice table is because you check the 5% rule, right? But with the Henderson-Hasselbalch, some people just put in that initial concentration into the Henderson-Hasselbalch, which really, strictly speaking, is for equilibrium concentrations. It should be this whole thing, but because you can generally ignore that X in most cases, you get away with it. All right. Now, any questions on any of this stuff that we just were talking about?
In this example, will we always get to not account for one of the like NaC2H3O2? You know how we didn't account for it because it was like a spectator ion. I don't know.
Yeah, we didn't account for the Na+.
Will it always be like that where we can cross out one of those?
Yeah, because it turns out that that's the way that you have to make a buffer. And maybe this is worth looking at a little bit. Again, remember I said if I put in, say, some weak acid in water, right? It comes to equilibrium with that water and its conjugate base. Oops, that's a plus. Sorry about that. Right now, and we mentioned before that, okay, it comes to equilibrium, but there's just not enough X minus for it to have a good buffer capacity. So it's really not a buffer. It's not a good buffer anyway, right? So how do we increase the concentration of the conjugate base? Anybody?
Common ion effect.
Yeah, you add in some sodium salt of that ion, which you know from Chem 200 that you get a spectator that you don't care about, plus more of the conjugate base that you do care about, so you can beef up the concentration of that conjugate base. And that's how you make a buffer. You add a weak acid. Okay, that's good, but I'm going to need more than that for the conjugate base. I need another source of the conjugate base. And like you said, the common ion effect, you add in some more of that X minus, and you do it with a spectator because you don't want to have to worry about some other reaction that's going to take place. Or if I have a buffer, say, made up of this guy, no, yeah, okay, so what am I going to add in here? In this equilibrium? What do I have to add in a source of? So this is a weak acid, right? Ammonium. It's weak, so the equilibrium lies to the left, but it does come to equilibrium. It's weak, so I do produce some ammonia, but it's still not a good buffer. I don't have enough what?
And ammonia, you need more ammonia?
Yeah, so I have to add in ammonia. And so I just add in some pure ammonia to beef that up. Kind of like I had to add in a salt of the base here. Another example might be, what if I start with F minus, like NaF, right, in water? Then I have that Na again plus, but I can ignore it because I know it's a spectator. And I form some HF and some hydroxide. But I know this reaction is going to lie to the left because I know this is a weak base. So what do I have to add into this equilibrium to make it a buffer?
More acid.
Yeah, so I have to add in some more of the weak acid. So I might throw in a solid HF or some solution of HF in water to beef up that. So remember, that's part of the definition of a buffer. You have to have a substantial amount of weak acid in the presence of its conjugate base.
Thank you. That clicks more for me.
All right, good. And if it doesn't, just keep asking and I'll keep trying. All righty. So this is kind of an initial buffer problem that we looked at. So we said we can use the ice table to find the equilibrium concentrations, check the 5% rule to make sure we can ignore, and calculate X from the relationship with the equilibrium constant Ka, in this case acetic acid. So once I find X, I know what the concentration of H plus is. And once I know the concentration of H plus, I can calculate the pH. So it's the old ice table. Or I can just take these concentrations, stick them in the Henderson-Hasselbalch equation, and calculate the pH. And I get the same thing because the 5% rule is in effect, and I can ignore that little bit of X that's added or subtracted. Any questions to that?
Yeah, I have one, Professor. So you said that doing the ice table is a safer fail-proof method.
Yeah.
In Chem 201, will we have any situations where, say, if we use the Henderson-Hasselbalch equation, it'd give us a wrong answer and we'd have to revert back to the...
Yeah, probably not, because we try to ensure, and if you do, it's a mistake. I made up a problem and I just didn't think it through or whatever, but we make them so that you don't have to do the quadratic formula, because that's kind of math stuff and it's really not testing on your chemistry. And if you make a mistake in the math, then that's kind of too bad, So we try to get away from that. Besides, you can always check your quadratic equation with those formulas online, and they'll do all the calculations for you. So that we try not to concentrate on the math and try to get at the chemistry as much as possible. So to answer your question, nah, probably not. All right, any other questions? But I would suggest it's good practice anyway. If you're going to use the Henderson-Hasselbalch, check it with an ice table. If you're going to use an ice table, check it with the Henderson-Hasselbalch. That way you get comfortable using both. I know you didn't probably want to hear that, but Oh, well.
Sure.
That's more work, damn it. Well, I say no pain, no gain. All right. This is kind of backing up again, taking a look at how we're going to solve, or hopefully how you're going to solve buffer problems. It's the 1-2 punch. You got a buffer. It's established. There's an equilibrium between some weak acid and its conjugate base. Then what happens when a base is added into the buffer? What's that first reaction? It's a completion reaction. It's a Chem 200 to neutralization. Here's our limiting reagent. That's got to be in the minority. That's the only way buffers work. You have to have a lot of the weak acid or a lot of the conjugate base compared to what's going to be absorbed. Okay. So this happens and it takes place to completion. Strong driving force for making water, that absorption. That's a Chem 200 limiting reagent. You lose the same amount. In this case, when you add a strong base, you lose that same amount of weak acid, the same amount of the strong base that you added, and you produce the same amount of conjugate base as the strong base that was added. And it's kind of the same thing for when a buffer absorbs a strong acid. The strong acid is the limiting reagent, and its amount is important because it's the same amount of the conjugate weak base that's used, and it's the same amount of the weak acid that's produced in this absorption. And you have to know these in order to recalculate the new concentrations that are left of the weak acid, then that are left of the conjugate base, so you can put them into the ice table to solve it, or you can put them into the Henderson-Hasselbalch and solve the new pH. Any questions on that? Oh, good. So let's talk through this one here. Okay, a buffer is made up of 35 milliliters of 1.30 molar acetic acid and 45.5 milliliters of 1.25 molar sodium acetate. Find the new pH after this number of milliliters of the strong base was added. And then I have this ice table set up here. Now, before we even get in there, I'm going to ask you some questions just to see if you can identify what's going on here. First of all, I got 35 milliliters of some concentration of this compound right here. So what is that compound? What's that called in this scheme of things? What can you identify that as being? What category?
Our weak
acid?
Yeah, so that's your weak acid. And then I have this thing right here. What's this?
That's what we add to make more of the CT of the conjugate base.
Yeah, so that's your source of conjugate base. So right off this, if they didn't tell you a buffer is made from, if they just said 35 mils of this and 45 mils of that, then already you're looking at it and you're saying, oh, geez, that's a common ion problem. That's a buffer problem. All right, so now we're setting it up. And I have my concentrations. But I'm mixing these different volumes. If I wanted to calculate the pH of this initial solution before anything was added to it, then I would have to go back to Chem 200 and remember my dilution laws, because I took 45.5 mils of this concentration of the conjugate base, and I mixed it with another aqueous solution. So its concentration is no longer 1.25. It's something less. It's diluted. And the same thing with the weak acid. It's something less because it also got diluted. So this question doesn't ask you to calculate that, but if you did have to do that, if you had to calculate the initial pH, you would have to do a dilution law calculation. You know, the M concentrated, V concentrated equals M dilute, V dilute. Okay. All right, now it says find the new pH after 5.02 milliliters of 0.13 molar NaOH was added. So now you're going to have the 1-2 punch. And this is actually the setup for the second part of the problem. The first part, before you even get to that, is that Chem 200 limiting reagent problem, right? So what I have to do is I have to calculate the moles of strong base that's introduced. So moles of strong base introduced. That's going to be, let me start with the concentration first. It's going to be 0.13 moles per liter of OH minus, right? The sodium is a spectator, so I'm going to ignore it. And I have to introduce 5.02 mils. So that's 0, 0 liters. And that's going to give me the number of moles. The next thing, I know that this hydroxide is going to react with which component? What's the strong base, the sodium hydroxide, going to react with?
The weak acid.
Yeah. And so that's the acetic acid, but I'm just going to abbreviate it and call it HA. And I know it's to completion. Strong driving force for making water and a salt. So there's sodium in there and there's A minus, but I can ignore the sodium. It's a spectator in that salt. All right. So I'm figuring out the number of moles that are going to react, and I'm going to need that. So 0.13 times 0.00502 equals 0.0006526. All right, and it's going to react with the weak acid. And according to this, I have a 1.30, and I have 35 mils of it. And you guys can check this on your calculators to make sure that I'm not making a mistake. So right off, you can see that the weak acid there's way more weak acid than the strong base that's being absorbed. So now I know how much HA is left over. I just have to subtract that amount from the amount of HA that was there. So I get that minus 0.0006526, and I get 0.0448 moles of HA remaining. And I have to add this much, that many moles, to the moles of A minus that were there, because that's how much was created. It's a limiting reagent. That's the limiting reagent. Okay, so that means I have to figure out how many moles of that weak conjugate base that was added in, and that's where I use those other numbers. So I have moles of weak base. That would be 1.25. And I have 45 mils, 45.5. So I get, and I hope somebody's checking me. That's initially, so I have to add this number over here to that because I'm producing that much more. And so if I did my calculator stuff correct, then I have 0.05758 moles of A minus. So that's after the initial reaction to completion, the Chem 200. I have that many moles of A minus. I have this many moles of HA. All the hydroxide's gone. And so now I can recalculate the concentration of A minus and HA and then put them in the ice table. Or I could put them in the Henderson-Hasselbalch. So these are moles. How am I going to calculate molarity? Because that's all you should be putting in an ice table. What am I going to need? Right? I'm
Total
going to
volume.
need, yeah, I'm going to need that total volume. So that's 35.5 plus 45.5 plus 5.02. 35 plus 45.5 plus 5.02 equals 85.52. So when I divide those moles, I want you guys to do this one. I should get those concentrations, and I'm going to do it and put it up there in the initial, and you try it too. I get 0.524. And 0.6727. Did anybody else get that? I hope.
Yeah.
Oh, that's good. At least we have one confirmation. So now you can just put those in the Henderson-Hasselbalch equation, which you should get the same value as if you figured out the ice table. And according to this little note I have down here, the pH should be 4.85. So X should be minus the log of X should be 4.85. So let's see. I have the Ka, which I'm going to have to look up because they didn't give it to me. This is acetic acid, so it's let me see. I'm just going to put the answer down here so I don't forget it. pH equals 4.85. So that's the answer. And I know that the Ka 1.8 times 10 to the minus fifth has to equal 0.673 plus X times X over 0.524 minus X. I'm going to neglect those X's, check the 5% rule. So X should equal I get for X 1.4 times 10 to the minus 1, 2, 3, 4, 5. So the pH is minus the log of X because X equals the H plus concentration. So I take minus the log of that, and I get 4.85. All right, any questions on that? So I think this is pretty much as complicated as a buffer problem is going to get. The only difference you might see, instead of adding a certain amount of strong base, you can add in a certain amount of strong acid, and then you're going to have to work through that, the logic through that. The strong acid is going to that time react with the conjugate base that's in the buffer. So that's the concentration that's going to go down initially. But you still have to do that Chem 200 limiting reagent problem first. And then you can go back and do the 201. So you see there's a lot of prep work to this, a lot of Chem 200, even before you get a chance to apply your equilibrium knowledge. Any questions on the buffer problem? So you should go back and study that and see if you can do it without looking at the answer. If you can, if you have to look at the answer, no biggie. Go ahead, look at the answer, think through the logic, learn why you're doing what you're doing, then put it away for a day or two, go back and look at it again without looking at the answer and see if you could work through that logic and see how many times you need to do that until you get through the logic. Once you get through the logic, then switch that sodium hydroxide to a strong acid, HCl, and work through that problem, or look for a problem like that in the textbook where you get the answer, and then do the same. All righty, now what I want to talk about is titrations, unless there's a question. All righty, here's a nice plot we have of pH versus the volume of a titrant. That's the thing in the burette. So I want to track pH as I add in more compound from the burette. In this case, we're going to be adding in 0.1 molar sodium hydroxide. And in the flask, there's 50 mils of 0.1 molar strong acid, HCl. So this is a strong acid, strong base titration. And you see that as I add in that base, the pH changes, but not very much. It's kind of slow in the beginning, right? And then you go through what's called an inflection region. And the inflection region is where there's a large change in pH. And then after the inflection region. And you see the equivalence point for a strong acid, strong base is right at 7. And that's what you should expect, because at equivalence point, you have an equal number of moles of acid and base. That's going to occur for this case right at 50 mils of the sodium hydroxide, since they're both the same concentration. And you started out with 50 mils of the strong acid. So the equivalence point should be at 50, where you have generated water and a salt. In that salt, you have NaCl, aqueous. You recognize both of these as ions of strongs. Therefore, they are so weak, they're spectators, and they're not going to change the concentration of hydroxide or hydronium in pure water, which in pure water, you know from studying the autoionization of water, that the concentration of hydronium and hydroxide is 10 to the 7th molar. So when you find the pH, which is equal to minus the log of H plus or OH minus, you can put in that value and you'll see that in fact that it equals 7. So all of that's in the titration curve, all that info's really nice. And you see that, you can use indicators to indicate the equivalence point. That's phenolphthalein. It changes a color from a pH of 8 to about 9.8. It goes from colorless to pink. Methyl red is somewhere down here at 4.5 to 6.3 or 4. And either one of these indicators will indicate the equivalence point. Now, why will they? And that's because of the shape of this titration curve. Now, notice you're putting in 40 mils right here. So the pH is way down here. And then you put in 40.5 mils. The pH goes up a little bit. It goes up a little bit here right before 50. But as soon as you hit 50, just one drop shoots the pH through this inflection region, which has in it contained that phenolphthalein molecule that changes color in the inflection region. So even though the equivalence point is here, that phenolphthalein is going to indicate that within one drop, and that's all you can hope for with the burette. So that gets you your endpoint within one drop. And the endpoint is your experimental determination of the equivalence point. That's when you stop the experiment. Any difference between the endpoint and the equivalence point is called titration error. It's just the error in your experiment. Any questions on the strong acid, strong base titration? Okay, there's a lot of information for you to process in there. So you need to go back and study all these little details. All right, let's move on. This is just a quick pick of, your starting point for a phenolphthalein titration. Endpoint is where there's a persistent pink, and then this is over the endpoint. This is your titration error. It just gets darker and darker. So you don't want this. You want to find it where there's a persistent pink that doesn't go away. Okay, the question is on this plate, why is the pH 7 at the end point or the equivalence point of a strong acid, strong base? Anybody?
Because the concentration of OH and H plus are equal.
Nope. Good guess, though. Thanks for playing.
Because you produce water and a neutral salt.
And a neutral salt. Why is that salt neutral?
Because they're conjugates of the strong
Yes.
spectator.
Yeah, thank you. Thanks. That's exactly right. Now, I heard this expression the other day about successful people. And the reason why they're successful is because they fail their way all the way to the top. What's that mean? That means they've just been doing stuff and they get it wrong. They get it wrong. They get it wrong, but they learn from it each time and they adjust. So they fail their way to the top. That's one of the traits of a successful person. So don't be afraid to fail or get it wrong. All right. So, okay. What else do we have here? We can, for a strong acid, strong base, we can use an indicator anywhere in that inflection region because that is going to change color for one drop, and that's the best that you can hope for with a titration using a burette that delivers one drop. Some notes on definitions. You can read those. This is the shape of a curve that would occur if you had an acid in the burette and a base in the flask. So you start out with a basic pH, you add in the acid, but there's an inflection region again, and you want to pick a indicator that's going to change color in that inflection region. All right, now let's introduce a weak acid titrated with a strong base. So we have something like sodium hydroxide again in the burette. And this time we have a weak acid like acetic acid in the flask where the pH probe is. And so we're going to start out with the pH pretty low. Now check this out. I have here the curve for the weak acid overlaid on top of the strong acid curve that we just looked at. So what's the difference? Well, of course, the pH is going to start up a little higher than a strong acid would. You see that this guy there's a slight rise in the curve, whereas the stronger one was flatter in the beginning. And you see that the inflection region for the weak acid is smaller than the inflection region for the strong acid. So for the weak acid, you could not use methyl red to indicate that endpoint because methyl red is going to start changing color right here at a pH of 4, which corresponds to only about 10 mils. And you know equivalence point isn't till 50, right? Equivalence point, it's 50 mils of this weak acid and 50 mils of the strong base. That's going to be required for them to have an equimolar amount. And that's where equivalence point is, at the equimolar amount. So phenolphthalein would work for the weak acid titration, but methyl red would not. Does everyone see that? All right. Also, you see that in this titration of a weak acid, the pH at equivalence point is above 7. It's not 7. Why is it not 7? I got a strong base plus a weak acid. That's going to go to completion. And I'm going to get water and a salt. So what is it in the salt that's making that pH greater than 7 this time?
The conjugate base.
Yes, the conjugate base, the A- of the weak acid. And if you had a strong acid and a weak base, you'd expect that equivalence point to be below 7 because of what we talked about when we were looking at salts and water and their pHs. So you have to look at that, the ions in the salt. Okay. And so this talks about that here on this plate, some more detail. And again, this talks about some of the differences between the two titration curves. So you should study that. This plate shows you how the titration curves change as you go from a strong acid to a weaker. You see, as you get weaker and weaker, the inflection region gets smaller and smaller, and you have to be really careful about that indicator. Some of them are so weak you can't find an indicator that's going to indicate the equivalence point, and you just have to use a probe or something. This is an example of a base that's polyprotic, so it can accept more than one protons, so it has several equivalence points for each one. An acid example you're going to look at in lab, say phosphoric acid, and you're going to have some sodium hydroxide that you're going to add to that, and it's going to have several equivalence points, and they correspond to the ionizable protons. Now, we're kind of running out of time here for this discussion, so tomorrow I'll pick it up here. But what comes next is titration problems. And the titration problems we're going to do, or you're going to do, are not any more complicated than any of the stuff that we talked about before. We're just going to have to recognize them and sort them out. So you might be, for a titration problem, you might be asked to calculate the pH before any, in this case, base was added. And then you're going to be asked to calculate the pH when some base is added. This is called the buffer region, because what you create here is some of the conjugate base of that weak acid. So here you're going to have some of the weak acid left over in the presence of its conjugate base. At equivalence point, you're only going to have that conjugate base in the salt. And then after equivalence point, the titration curve is dictated by the strong base that's added. This guy, you don't even have to worry about anymore because it's a weak base and it's not going to add significant amounts of hydroxide. So we're going to take a look at all those different situations. And that's about wraps it up for our time. You guys have any questions?
No, thank you, Professor.
Okay, guys,
Thank you.
you got it.